Hello, hello. This is David McMayer with Southwest High School, and we are going to be talking today about special right triangles. So this is section 6.1. You can add a section to your table of contents in your notebook, and then open up to a new page. When we are talking about special right triangles, what we're really talking about is similar triangles. Okay, so special right triangles are just triangles that we can use some basic geometry to try and figure out missing side lengths. Kind of a broader study of that is trigonometry, where we can use some proportional reasoning to find missing side lengths. So you don't need to add these pictures to your notes specifically, but what I wanted to show you is just this and call to attention. We can use this idea of proportional reasoning to find missing side lengths on triangles. Like if I tell you that little triangle in the middle is half as big as the triangle on the left, and then I tell you some of the dimensions on the triangle on the left, you can find the missing dimensions in that small middle triangle. And likewise, if I tell you something about the bigger triangle, like if I tell you it's 1.5 times as big as the triangle on the far left, you can do something with that, and you can find missing side lengths. That idea of proportional reasoning is very important as we move forward and think about trigonometric reasoning. Okay, so we're going to be using that. Today, specifically, we're looking at proportional reasoning with similar right triangles that are special. Okay, so the first special right triangle we're going to look at is a 30, 60, 90 triangle. And it's kind of born out of an equilateral triangle. So I want you to write this down, that draw your best equilateral triangle. And I think some things that we know about equilateral triangles right off the bat is that all the angles are the same. And if we know the three angles in a triangle add up to 180 degrees, that means all of these angles must be 60 degrees. Now, I don't know how big that triangle is, okay? But I do know that all the sides are the same. And what you can do with that, and I have it already drawn there, but what you can do with that is cut this triangle in half. So I'm just going to write cut in half. And like literally cut it in half, like right down the middle. Okay. What's going to happen there is that you're going to wind up with a right angle in that bottom right-hand corner. The angle in the bottom left-hand corner is still going to be 60 degrees. And then the angle in the top corner is going to be half of 60 degrees or 30 degrees. Now, this is a good thing because what we have then is three angles in this triangle that add up to 180 degrees. Now, we can do some things with this. I know that the hypotenuse of a right triangle is across from the 90-degree angle. So this is called the hypotenuse. And then because we cut that equilateral triangle in half, I know for certain that this is going to be this shortest side, the side that's across from the 30-degree angle, is always going to be half of the hypotenuse. That idea is hugely important when you're thinking about 30, 60, 90 triangles. So we can take that triangle, and I'm just going to grab this triangle here and make a little copy and move this over. I think draw another triangle. We're going to put in some examples here of some special right triangles, and then maybe talk about some of the side lengths that you can have there. I'm going to draw them all the same size on my paper, but I'm going to label the side lengths differently. Okay, so I'm going to start out with this one. And, I'm just going to say that I'm going to call this a unit right triangle. Unit just meaning that one of the side lengths is 1. Okay, so I'm just going to say that this shortest side is 1. This is, of course, a triangle that has angles 30 degrees, 60 degrees, and 90 degrees. Now, if that shortest side is 1, I know that shortest side is half of the hypotenuse. Therefore, this other hypotenuse must be 2. See, I'm using some proportional reasoning there. The other thing that I can do here is take that same triangle and heck, I could make the hypotenuse 1 if I wanted to. So now keep in mind, I'm drawing this to look like they're identical, but I can say not to scale, and then just say this hypotenuse over here is going to be 1. Therefore, the shortest side is going to be half of the hypotenuse. I'm using some proportional reasoning to cut the side lengths in half. Now, yeah, we haven't done anything with that third side yet. Let's go get that third side. If I wanted to know this third side on the first triangle that I had, this is a right triangle, so I can use our favorite theorem about right triangles. The sum of the squares of the two shortest sides, the two legs of the right triangle, is equal to the square of the hypotenuse. It's the Pythagorean theorem. Okay, so I could, little scratch work on the side here, I could write x squared plus 1 squared has to be equal to 2 squared. That really quickly turns into x squared plus 1 is equal to 4, which turns into x squared is equal to 3. A little square root on both sides of that equation, and you're going to wind up with x is equal to the root 3. So I can erase this x and replace it with a square root of 3. Hey, remember when we cut all the side lengths in half to get to our second triangle? You can cut square roots of 3 in half. You just divide them by 2. You write a fraction. Square root of 3 on top, 2 on the bottom. Okay, so we've got some triangles there where the side lengths of those triangles are 1. These are called some unit right triangles. You know what? We can even take these triangles and we can make them bigger or smaller. I could take all the sides of this this triangle that I have here. This is the representative triangle that I use most often. But I could take all of these side lengths and I could multiply them all by anything I want. Okay, so I can take all of those side lengths and I can multiply everything by 6 if I like, or I can multiply everything by 15, or multiply everything by 1/3, or it doesn't matter. And then I can make a same size triangle, a same shaped triangle that is a different size. You know, one thing you could do, and I'm just spitballing here, but one thing we could do is multiply everything by the square root of 3. You're like, oh my gosh, McMahon, why would you do that? Here's why you would do that. If you want to kind of compare this triangle with another triangle where this longest leg, that side that's across from the 60-degree angle, happens to be an integer, well, then you don't want to use a square root of 3 to compare that. You'd want to have like a whole number there. So multiplying by the square root of 3, and this is a little bit of a lesson with radicals. If I have two radical expressions multiplied together, that's actually equal to the square root of the product of those two radicands. And 3 times 3 is 9. The square root of 9 is 3. So all of this right here becomes 3. So I'll just get rid of all of that and just say that that's going to be equal to 3. And then these other parts are going to be 2 times square root of 3 and 1 times square root of 3. So if I wanted to kind of clean that up just a little bit, I'd have a special right triangle that has a 2 root 3 on the hypotenuse and a 1 root 3, often written as just square root of 3, on the shortest side across from the 30-degree angle. So these are all special right triangles here. They're all 30, 60, 90-degree triangles, and I can use those then to compare to other figures. Another special right triangle that we talk about is a 45-degree, 45-degree, 90-degree triangle. And in this particular case, we're not cutting anything in half here. We're just recognizing that this is an isosceles right triangle. So I think that's important to write down, that this is an isosceles right triangle. So we've got a 90-degree angle. We've got two 45-degree angles. Not 44, 45. So the things that I know about this triangle is that we've got some sides that are the same, and we certainly have some angles that are the same there. And then I can try to do something with that. Okay. So I could take this shape now and copy that shape, and we could make some of our own unit triangles. Okay, these would be representative triangles that we can then use to compare to other triangles and make some, use some proportional reasoning. So if I make the shortest sides both 1, the sides that are across from the 45-degree angles, then the hypotenuse of that triangle, boy, we could use the Pythagorean theorem again. Okay, so we did that before. So if this hypotenuse is x, we would say the hypotenuse squared is equal to the sum of the squares of the other two sides, 1 squared plus 1 squared. And 1 squared is 1, 1 squared is 1, put them together, you get 2. So x squared is equal to 2. Hey, x is equal to the square root of 2. So I can replace this hypotenuse that I had, where I put an x before, I can replace that with the square root of 2. Those would be the side lengths of the triangle that had a unit measure, a 1, along the shortest side. And if you wanted to make a new triangle that was bigger, you could certainly take all of those measurements and multiply by anything you want. So we could multiply all of this by 6, for example. I'm just making this up, but we could multiply everything by 6. So it'd be a 6 times a 1 and a 6 times a 1 and a 6 times a square root of 2. You don't really usually write 6 times 1. You just say that's 6, of course, but those two triangles are the same size. It's just one is 6 times bigger than the other. If I wanted to compare this triangle to another triangle where the hypotenuse was an integer, I wouldn't want to use a square root of 2 to compare. I'd want to, first of all, take that triangle and multiply all the side lengths by the square root of 2. So I'd multiply everything by the square root of 2. And what I hope you can see is that along the hypotenuse, you'd have a whole value of 2. And then on the other two side lengths, you just have a square root of 2. I can clean that up and move these around just a little bit for you. But these triangles that I've drawn here, those are all the same shape. They're just different sizes. And then just kind of realizing in your head that square root of 2 is just an exact representation of a quantity, a value. You can get an approximation on your calculator, type in square root, put in a 2, hit enter, and it'll be about 1.414 ... There's some other stuff, but it's a little bit more than 1.4. Square root of 2 is bigger than 1, but smaller than 2. Okay. All right, let's try to apply this to some problems. So far we've got the notes for this is what it all means. Let's try and do something with this. So if I was going to try to find the missing side lengths on this triangle, because that's really the problem here. We give you an angle, we give you one side length, and then you're supposed to be able to find the other two side lengths. Okay, so you can't use the Pythagorean theorem like right away here, because that would say x squared is equal to y squared plus 12 squared, and that doesn't really give you a lot of information about what x and y are. It tells you that there's a relationship between x and y. So we're going to draw in our one of our representative triangles. And I got to be honest, like I always, when I'm thinking about this, I always start with this unit triangle where the shortest side of this triangle is 1. You could start with the triangle where the hypotenuse is 1 as well. I like this, so then I can say that all the side lengths are integers. Oh, excuse me, all the side lengths are 1, 2, and then square root of 3. Square root of 3 is not an integer. And now I can start to compare. I want to try to take that triangle and kind of grow it into the triangle that I see here. So I think the first thing I'm going to do is make a new triangle here that is the same shape, but it's going to be a different size. So I'm going to multiply by square root of 3. And if I do that, just take all the side lengths and think about multiplying by the square root of 3. So 2 times square root of 3 is 2 root 3. Square root of 3 multiplied by the square root of 3 is 3. And then 1 multiplied by the square root of 3 is square root of 3. And now if I wanted the side that's across from the 60-degree angle, I forgot to write my angles in. If I wanted the side across from that 60-degree angle to be 12, well, proportionally, to get from a 3 to a 12, I need to multiply by 4. Okay, so my new directions here are take this middle triangle and multiply it by 4. So 4 times 2 root 3 is going to be 8 root 3. And then 4 multiplied by square root of 3 is 4 times square root of 3, or just 4 root 3. And of course, 4 times 3 is 12. And now I could compare and just see that y would have to be equal to 4 root 3, and x would have to be equal to 8 root 3. So that's using some proportional reasoning there. I got to be really honest with you. If you just wrote down the representative triangle and you had this original triangle, you can compare there too. Okay, so we could write an equation, and that equation would be x divided by 12. That's a ratio in the original triangle. I'm going to put the missing side length on the top of that fraction, just because it makes the algebra a little bit easier later on. And then that would be equal to, compare that to our unit right triangle here, 2 divided by square root of 3. Now that's kind of a nice equation, okay? If I take that equation, I can multiply both sides of that equation by 12, and the result of that is going to be, I'll do it over here. The result of that is going to be x is equal to 2 times 12 in the numerator divided by the square root of 3. So x equal, wait a second. I thought x was equal to 8 root 3, not 24 root 3, 24 over root 3. Well, if you type those into a calculator, you get the same decimal approximation. Don't believe me? Give it a try. Okay, so what you can do algebraically here, and you can kind of reason through this, if you take this pink number, this 24 divided by the square root of 3, and you multiply this by square root 3 on top and bottom, that yellow number that you see there, that's equal to 1. So it's like taking the pink number and multiplying by 1. You're not going to change it. You are going to change how it looks, though. In the denominator, we're going to have root 3 times root 3. We already know that that's equal to 3. In the numerator, I can't really combine those two parts, but I can juxtapose them. I can just say this is 24 root 3. And now this fraction has a 24 in the numerator and a 3 in the denominator. 24 divided by 3 is 8. Okay, so that's how we get from a 24 over root 3 to an 8 root 3. Now, the reason that we do this sometimes dates back to thinking about slide rules, and the fact that in a slide rule, you could divide by a whole number, but you couldn't divide by an irrational number. So in their tables of values, they didn't have a way to make that happen. So this is part of the reason that we still in math classes ask you to rationalize the denominator. But quite honestly, in terms of a value, 24 over root 3 is the exact same thing as 8 times the square root of 3. So same value. What I'm showing you here is just you can, with the triangles, you can proportionally reason your way to the exact same triangle, and then just read off what the side lengths are. Or you can set up a unit triangle that we had here in the beginning, and then compare that to an equation, and then algebraically reason your way to missing side lengths. Of course, once you know that x is equal to 8 root 3, then the shortest side is just half as big. So that would be 4 root 3. Let's try that with a couple of other problems here. So I just thought it was sort of puzzling, which of these triangles is bigger? A 9 on the side across from the 45-degree angle, or an 11 on the hypotenuse? Let's take a look and see if we can't figure that out. So I'm going to compare this triangle to one of our unit right triangles. So our representative triangle here is going to be a 45-degree, 90-degree triangle. I'm going to put a 1 on the hypotenuse. I said that wrong. A 1 on the shortest side. And then I know the other side would be the same. The other shortest leg would be the same. And the side across from the 90-degree angle would be the square root of 2. So if I want to grow this triangle to make them match the original picture, I would just have to take all of the side lengths, and our direction here would be to multiply by 9. So 1 times 9 is 9. That would be the same on the two shorter sides. And then 9 multiplied by the square root of 2 is just 9 root 2. Okay, so I think it's from here we can just very quickly reason that our shortest side, n, here would have to be 9, and then the longest side, the hypotenuse, would have to be 9 root 2. Okay, now you could certainly set up an equation there. I think n has to be 9. That's you could say I'm going to solve that by inspection, just by looking at the triangle and saying those sides have to be the same. If I'm going to set up an equation for m, I might say m over 9 in the first triangle is equal to the square root of 2 over 1 in the second triangle. I think it's pretty quick for you to see that if I multiply both sides of that equation by 9, m is equal to 9 root 2. All right, let's take a look at number 6. And for this particular problem, we've got a hypotenuse of 11. So if I'm going to do the grow the triangle method here, or draw the triangles in a different sizes, same shape. So I've got my 45-degree triangle where I'm going to make the legs both 1 and the hypotenuse is the square root of 2. I want to compare those hypotenae. Is that how you say that? And those two lengths, one is a whole number and one is irrational. So I think the first thing I'm going to do here is draw a new right triangle where the hypotenuse is a whole number. So I'm going to multiply everything by the square root of 2. So I'll have a 2 on the hypotenuse and then root 2 on the two shortest sides. So here I'll write my directions. Multiply by square root of 2. I don't like that. Sometimes we try and use notation and it doesn't quite work out. So I'm just going to write it out. Multiply by root 2. And if I want to, take it one more step here, I have to think like 2 multiplied by something is 11. Well, that something is 5.5. or 11 halves. So if I multiply by 11 halves, and I'll kind of go down this way, my new triangle, same shape, different size, and I'm just noting the size difference by writing the different lengths on the side here. 2 multiplied by this blue 11 halves is going to yield an 11. And then square root of 2 multiplied by 11 halves, I'm going to think about the other way around. 11 halves multiplied by the square root of 2 is 11 root 2 in the numerator and 2 in the denominator. So now I've got my triangle, and I can compare these two triangles, the original triangle that I had over here, and my new triangle that I made by kind of multiplying side lengths a couple of times. And I can see that x and y are the same, and they're both 11 root 2 over 2, or 5.5 root 2. Okay, and then if you wanted to do this with an equation, of course you could say x divided by 11, or y divided by 11. It's going to be the same solution both times. X divided by 11 would equal, and then I need to kind of compare here. X is our shortest side, or our leg of our right triangle. 11 is the hypotenuse. I've got to have the same ratio set up in my other triangle. So I'd have a 1 over root 2. So in this case, if I multiply both sides by 11, I'd get x is equal to 11 over root 2. Wait a second, that's not the same thing that we had over here. Oh, that's right. I need to multiply the top and the bottom of this pink fraction by the square root of 2 to rationalize the denominator. I'm just multiplying by a yellow number 1 there. You see it? Okay, so I'm not changing the value of the pink number. I'm changing the way it looks. So now this pink number could be written as 11 root 2 in the numerator and square root of 2 in the denominator. Okay, well, I hope that gives you a few things to kind of think about here with special right triangles. The ones we're really worried about here, and special right triangles is just, triangles where we can take advantage of some geometric properties to find missing side lengths, along with the Pythagorean theorem. And then we're just really using proportional reasoning. Okay, so we've got our 30, 60, 90 special right triangle and our 45, 45, 90 special right triangle. And we can use those to find missing side lengths on some triangles. Hope you have a great day.